Hello, and welcome to the first video lecture for Chapter 4. In this lecture, we're going to cover sections 4.1 to 4.2. This basically is going to introduce Newton's three laws, and we're going to do some simple examples, simple for the most part, to really illustrate what those three laws are all about. All right, and the laws have the boring names of Newton's first law, second law, and third law. All right, so let's just get right into the key terms. Okay, so our key terms are going to be defining the laws and a couple of other small topics. Okay, so Newton's first law is the law of inertia. All right, that's kind of the way you should remember it. Is the law of inertia. It states that if no net force acts on an object, then that object cannot change velocity. In other words, it states that a constant velocity is only possible if zero net force is present. Yet more, it defines that only a force can change velocity. So it establishes what a force is capable of, and it establishes what I like to say, that forces are the y of motion. You can't have motion without force, because everything would just stay at rest indefinitely in its an initial state of rest, right? How do things start moving in the first place? Forces. How do they change their movement? Forces. Okay? Now, do notice that the Newton's first law, commonly known as the law of inertia, has that word inertia in it. Okay? We've mentioned a non-inertial reference frame when we talked about acceleration, but what is inertia? Well, let's mention mass and circle back around. All right? So mass is matter, right? Simply put, that's probably what you expected, right? It's made up of atoms, okay? And in translation, mass is inertia, okay? Translation is motion in the x, y, and z directions, okay? That's what translation is. Translation is not rotation. More on that later, okay? Don't worry about that for now, but translation is simply motion in x, y, or z, or all of the above, okay? And thus mass is the sluggishness of matter, okay? That's what it represents, okay? Now it's interesting to be talking about this because we kind of take for granted that we know what mass is, but we haven't actually introduced mass. We've done a lot of motion physics, acceleration, velocity, changes in acceleration, all that, all these trajectories and whatnot, but we haven't talked about mass. We just simply haven't. Now we are. Okay, so now we can acknowledge that our particles have mass. All right, moving right along. Newton's second law. Newton's second law is the law of acceleration. Again, kind of the common name for this particular law. Okay, so we should expect it to be talking about acceleration. Okay, now it states that acceleration is directly proportional and parallel to net force. Okay, so that means that's giving us a relationship between something we've seen before, acceleration, and something new, force. Net is a word that just means sum, total. Okay, and the fact that we're saying that acceleration is proportional and parallel to net force, that's telling us that force must be a vector. Okay, and indeed we'll see that in the equations. Furthermore, Newton's second law states that acceleration is indirectly proportional to mass. So the more mass, the less acceleration. The more force, the more acceleration. Okay? All right? And finally, Newton's third law is the law of action and reaction. Okay? It states that for every action force, there is a reaction force that is equal in magnitude and opposite in direction. People often say that for every action there's an equal and opposite reaction. Obviously, they're leaving out some of the details that make that maybe useful to solve quantitative problems. So that's just why I'm making it very clear: equal in magnitude, opposite in direction. Okay? Also known as the law of force pairs, which takes us right to the definition of force pairs. What is a force pair? Well, it is a pair of forces that represent an action and reaction. Okay? Now here's an important rule about them. It must act on two different objects. So you can't have a force pair where one force is, say, the force at the top of something, and the other force is the force at the bottom of that same object. Okay? That couldn't be a force pair because those forces could not represent an action and reaction. An action and reaction must occur between two objects, or two particles, or two bodies. However you want to think about it, right? Because those are very much interchangeable terms, at least for our purposes currently in the class. Particle, object, body, okay? And in fact, we're going to see that term body more in this chapter, for like free bodies, okay? Just think object, okay? But not to get derailed here, a force pair must act on two different objects, And that's going to become front and center in some of the examples I'm going to show you. You're going to see the importance of that, okay? And kind of an easy mistake that could be made, that I've seen made, where people think something is a forced pair that is not, in fact, a forced pair. All right, well, let's look at the laws in equation form. Well, the first one is Newton's first law. Okay, so as an equation, it simply states that the velocity vector is constant if and only if the net force vector is equal to 0. And the if and only if is a mathematical expression that means that we could read this sentence either way. We could read it in this direction or in the more traditional from left to right direction. Okay? And it's true, right? And that just is consistent with the definition I had above on this page. All right? Next up is Newton's second law. Now I included an alternate notation here, which is this here. This is sigma for sum, so this would be the sum of forces. I don't really use this notation, and so instead I prefer, and I have grown to prefer, using F with net to denote the sum of forces. So net is a total, okay? And notice here I'm just saying that net force equals ma. That's it. F equals ma. That's Newton's second law, okay? Now it's a vector law, so it's F net vector equals ma vector. And this is another one, right? People tend to know F equals ma if they know any physics equation, but they often don't say F net equals ma. That's important because it's not like an individual force equals ma. What if there's more than one force? Okay? Each force doesn't create its own acceleration on an individual particle. That means an individual particle and object would have to have multiple accelerations. That's impossible. You can only have one acceleration per object, particle, or body, right? I mean, just think about it. So it's got to be the total of all those forces. That is the collective force that we're concerned about. All right? And Newton's second law also really showcases the units of force, because we can clearly see that it's m times a. We know that the units of m are kilograms. Okay? That's just the SI unit of mass, kg. Okay? And then we know that acceleration is meters per second squared. So then the units of force is kilogram meters per second squared, which we call N. This is a derived unit, and it's called the Newton, okay? Or just N for short. All right? This next equation is just reminding you that the net force vector is indeed a vector and can be split into components relative to whatever axes you want, in this case, x and y. All right? So it's a good reminder, it is a vector, can be split into components, and all of our forces, all the problems that we're going to be doing, and we're going to be doing plenty of complicated problems with our forces, are going to be always 2D. But that's pretty much true for this class anyway. But really, we don't have to worry about anything being 3D. Okay? And then finally, Newton's third law. All right? And this simply states that, well, maybe it's not simple, right? Let's think about the notation. This is a force vector, and this notation reads A on B. Okay? So this is the force on B on A by B. See, it's not, I mess it up, right? So it's the force on A, because that comes first, by B. Okay, so it's on is the first letter, by the second letter. So on A by B. Okay, that's how you read a subscript like that. Okay, it's kind of similar to the subscript for relative velocities, right? Whereas two letters and we kind of read it in a certain way, something relative to something else. But in this case, it's force applied on something by something else. Okay? And that's saying that that force is equal in magnitude and opposite in direction, because if you multiply a vector by -1, put a negative in front, that means you're just flipping it 180 degrees, which is known as anti-parallel. All right, so that's the opposite in direction part. And the fact that this is the same number, right, that this is a true equation, means that they have to be equal in magnitude. Right? So that's Newton's third law in vector equation form. All right, well, let's get on to some examples. All right, so there's only two types of problems, okay, in this first set of introductory sections for chapter 4, and that is problems that involve Newton's second law, all right, and use one or more kinematic equations, and problems that involve Newton's third law, okay, and a force pair that causes two separate bodies to accelerate in one dimension. All right, so these are really the types of problems that fall into this category of kind of introductory problems to illustrate the basics of Newton's laws. Notice there's no problems to really illustrate the basics of Newton's first law, because it's simply something that moves or it doesn't. Okay, it does kind of have to do with equilibrium, but we're not really talking about that right now. Also notice that problems involving Newton's second law will always involve kinematic equations because otherwise they're simply F equals ma and there's not much to do in terms of an actual problem that could really be worth practice, okay? And then as far as the type 2 problems, notice that they always involve two separate bodies. Well, that's interesting because that's kind of cheating because in a sense, if you look at the chapter, everything moving forward, so the next 3 or the next 2 lectures, don't mention anything with two bodies. And then finally, the last lecture, which covers the last section of this chapter, specifically calls attention to two-body problems. Makes a big deal about them, but yet we're going to do them here, right? Are we jumping ahead? Yes, a little bit, but we're doing it so that we can illustrate Newton's third law, okay? But we're not doing it in the same way necessarily. We're not considering all the forces and details and angles that we do in the two-body problems at the end of the chapter. So there's a trade-off, okay? All right, well, let's get into the examples. Starting, of course, with a type 1 example illustrating Newton's second law and using some kinematics. All right, so example 1. A 10 kilogram box is accelerated from rest by a net force that is applied constantly for 4.4 seconds, and that box is found to have a final velocity of 14.5 meters per second. What is the magnitude of the force acting on the box during the period of acceleration? Okay, so we're going to use kinematics to find A, and then use A to find F. Okay, so let's do that. So based on the information that we're given, I know that I'm going to be able to find A based on V and T. So there you go. I'm just going to solve for A. And let's plug in our numbers here. All right, so we end up with 3.3 meters per second squared based on the two values I was given. Okay, so then the next step is to use Newton's second law to find force using the A that we found in the first step. Okay, so we'll just use F equals ma. Just plug in 10 kilograms times the acceleration we found. We're done. 33 newtons. So as long as we applied a constant force of 33 newtons, we get a constant acceleration of 3.3 meters per second squared, and we would achieve the final velocity that we were looking for in the time that we were given. Okay, make sense? All right, so if the same force found in the previous example acted for the same amount of time, but on a box that had a mass of only half as much, what would the final velocity of this lighter box be? Okay, well, what do you think it would be? If it's half as massive, so 5 instead of 10 kilograms, how fast do you think it will be at the end? Twice as fast, maybe? Let's see. Okay, so use Newton's law to find acceleration because we're working backwards this time, because this time we're starting with a known of 33 newtons. And we find out that using the 33 newtons but dividing by the smaller mass, we get a larger acceleration. And then use kinematics, okay, see how we're just simply going backwards. And then we'll simply take our larger acceleration, multiply by the same time, 29 meters per second. Well, sure enough, twice as fast. All right, because this object is half as sluggish, okay? Right, that was the term for sluggishness of matter, right? Okay, and then finally, what if that same force, again 33 newtons, was applied to the half-weight box, so the 5 kilogram one, but for half the time? Okay, so we found if it was applied for the total time, we got to, that looks linear. That's like the equation of a line, right? Y equals, b plus ax or whatever, right? Intercept plus slope times height or vertical. So if it's linear, then cutting it in half, and then cutting something else in half. It seems like the two effects, will either give us a quarter if we're multiplying by them, but if we're dividing, they should cancel out. And we are dividing, aren't we? Let me show you. Okay. So since we already know acceleration, we're simply going to plug it in because we already know acceleration because it's the half-weight box. But we're going to plug in half the time. So instead of 4.4 seconds, it's 2.2. And we get back to a final velocity of 14.5, just like in the original statement. All right, why does that work? Well, let's think about it, right? So velocity is acceleration from time, assuming that initial velocity was 0, which it was in this problem. And then acceleration is just F over m. Well, in this case, our half-weight box is 1/2 m naught. I'll zoom in a bit, right? So our m is 1/2 m naught, because it's half the original weight box. And our time, our t, is 1/2 the original time. So then the 1/2s cancel out, and we're just left with F over m naught times t naught. Well, that, of course, then will just give us our original velocity, because that's what we started with. Okay? Our original statement. All right, so example 2, I had a bit of a mistake, so I'm going to add something. I forgot to stipulate the mass of the car, and you can't solve the problem if you don't have the mass of the car. Right? We're not doing kinematics anymore. I have to give you masses. So sorry for that, but I added it in here retroactively, handwriting it in. So let's just go through it, not a complicated problem. A car is traveling at an initial velocity of 33.9 meters per second, begins to apply some brakes, thus creating a constant negative acceleration. If after the car has traveled 413 meters, the velocity of the car is 14.7 meters per second, so it's slowed down substantially, what force do the brakes exert? And we're obviously going to assume a constant force and a constant acceleration. Wasn't specified otherwise. So we use this kinematic equation. Why? Because we have a final velocity, an initial velocity, and displacement. So we can solve for A. So that's what I'll do. I'm just going to solve for the acceleration, plug in my values, and I get a negative acceleration, which makes sense because the car is braking. All right, and then I'm going to find the force of the brakes. All right, plug in our number. I'm going to, again, stipulate this as a negative force because it's force is a vector and it is a braking force. All right, it is a force that is opposite the direction of the initial velocity and the final velocity. All right, and the displacement for that matter. And those are all positives. And then here I plug in my mass, 1,000. So then I just get a braking force of negative 2,260 newtons after I round to 3 sig figs. All right, so like I said, pretty straightforward problem. All right, let's draw some pictures. So these are some concept checks to kind of think about, what are all these force problems? What are we going to be seeing? Kind of a preview of things to come. Identify the forces and their names in the following situations. You might not know all these forces and their names, so if you're just trying to do this on your own, but I'm just going to walk you through them. So an elevator is suspended by a cable and descending at constant velocity. All right, so here's our elevator. Well, the forces we have is a tension force. We'll be talking about that in a later lecture in this chapter. And then Fg is just the gravitational force, okay, which is a synonym of weight. So gravitational force and weight are interchangeable terms, okay? It's important, okay? And then what about a compressed spring that is being pushed or is pushing a block across a rough horizontal surface? All right, so we got a bunch of forces here, kind of interestingly, right? So we've got the force of gravity, which I don't re-identify, okay? We've got Fs, that is the spring force, okay? Sometimes that's called the restoring force of the spring. It is a reaction force. You push on a spring, the spring pushes back. We usually call that the spring force, all right? Then we've got the friction force, okay? This is a contact force that's created by microscopic phenomenon, okay? But we kind of give it this empirical definition, this kind of experimental definition of calling it the friction force. Different surfaces have their own friction forces and their own friction coefficients. More on that in this chapter. And then we've got something called the normal force that points up. The normal force is another reaction force. The weight of the block pushes on the table pushes back with the normal force, okay? All right, so let's name some more forces. A brick is falling from the roof of a 12-story building with negligible air resistance. Oh, well, that's just gravity. The only force acting on that block is gravity, okay? It's accelerating. It's a single force situation because there is no resistance force, okay? How about a boat is accelerating from rest across a placid lake? All right, so what are the forces there? Well, we've got the gravitational force again. We have a friction force, right? We could also call that a drag force because it's a fluid, okay? So often it's called a drag force. Then we also have a buoyant force. So buoyant force is always given a special name. The buoyant force, however, basically plays the same role as the normal force. It's just that the normal force is from solid surfaces like tables, and the buoyant force is from fluids. But they're both reaction forces that are driven by an action force of gravity. Gravity is pretty important, okay? And then finally we have a thrust force because the boat is accelerating after all right? And so that's the idea of a thrust force. Thrust forces are, you might think, oh, what are they? Or, are they like an exception to the rule? Really, they have more to do with momentum than anything else. But of course, momentum, Newton's third law, are kind of interchangeable. But I haven't seen that yet in this class. If you've seen it before, that's fine. If you haven't, that's fine as well. But we'll talk about how we can kind of talk about the idea of thrust and conservation of momentum in kind of the different ways, right? And we have a whole chapter where we get into momentum. So we definitely will have time and space to do that. Okay? And finally, a communication satellite is orbiting the Earth every 120 minutes in a stable circular orbit. All right? So that's actually just the force of gravity as well. Right? This is my communication satellite here, right? With its long solar panels. So the idea there is that this satellite, just like the block falling off the 12th story of the building, is in free fall. Only a single force is acting on it. Okay? There's no other force acting on the satellite. In fact, the only reason the satellite doesn't hit the ground is it's moving so fast to the side that its curved projectile path matches the curvature of Earth. But it's just in free fall, okay? Just like a projectile. Pretty amazing, right? There's no separate force to maintain orbit or something. Okay, So now let's get into our Newton's third law examples. These are going to step up in increasing complexity. All right, so two people of equal mass of 70 kilograms each are standing on perfectly smooth ice and are holding the two ends of a taut rope of negligible mass. And that's basically true of all the ropes that connect, rope, strings, cables, whatever you want to call them, that connect objects and the problems in this chapter. There's quite a bit of that. Sometimes those ropes / strings are across a pulley, okay? But they're always of negligible mass. In other words, zero mass. One person pulls with a pulling force of 350 newtons, while at the same instant the other person simply holds on. If the length of the rope is 12 meters, how far will both people travel by the time they meet? So first we kind of want to get over some conceptual hurdles about what it means for one person to just hold on, and then actually solve the problem. Okay, so first let's get our picture. All right, there it is. All right, so here we have our picture. Here are two people, person A and person B. I'm defining positive x as towards the right. All right, their masses are the same, so I could just call them m, and they're equal to 70 kilograms. The distance between them, d, is the 12 meters that was referenced in the problem. Okay, now what's going on, right? What are our forces? So the idea is that one person holds on to the rope while the rope pulls on them. The other person pulls on the rope and the rope pulls back. Okay, so that means that we have two force pairs. We've got FAB equals negative F hold and FBA equals negative F pull. All right, and that's okay. So let's think about that, right? Because what happened in the one case is the rope pulled on the person, thus the person pulled back on the rope. That's this one. Whereas this one, someone pulled on the rope and the rope pulled back on the person. In both cases, two objects, equal and opposite reactions, okay, or forces. One's an action, one's a reaction. Okay, so that is Newton's third law. Okay, now what we really care about though is how do we relate FAB to FBA? Because these subscripts imply that maybe these are the force pair, right? And I excuse that maybe the confusion of the subscripts, but really those subscripts do make sense because we'll find that this is the force on A by B, and this is the force on B by A. But how's that possible? Well, let's think about the net force on the rope itself. Zoom in a tad on this, there we go. Well, the net force on the rope is F pull, okay, towards the right, minus F hold towards the left, and it equals 0. Why? Does it equal 0 because these represent a force pair and they're equal and opposite? Well, certainly not, because they're two forces acting on the same object. So they definitely don't represent a force pair. But they equal 0 because the mass of the rope is 0. So since the rope doesn't have its own inertia, it is essentially this isn't a technical term, but it's essentially like a perfect transmitter of the force. It means that it might as well not even be there. Okay, now of course it has to be there because that's the only way for the people to, kind of move towards each other and to have started 12 meters apart in the first place. But by giving it negligible mass and treating that mass as 0, it really isn't there. Okay, it's just like this magical connection between them. All right, but again, it's an approximation, but a good one, because the rope very well could have so much less mass than them that it wouldn't significantly alter the actual calculations. Okay? But that's why we can get away with saying now that since F pull equals F hold, and then we refer back to these ones, that means that FAB also equals FBA, at least in magnitude. See that? Okay. So then we set up the net force on both people. So the net force on A is just force AB, okay, and that's going to be in the positive direction based on the coordinate system chosen. Meanwhile, the net force on B is negative FBA, okay, and then we'll just solve for A sub A and A sub B, okay. Now if I go ahead and solve for their magnitudes, I'm just taking their absolute values here. And in this problem, I choose to kind of represent a few things as absolute values since we care more about distances than displacements, all right. And so then I'm going to find that both person A and person B, since they both have the same mass and they're both experiencing the same force, must both have the same magnitude acceleration. Okay, so then we're going to find out how far or how much time it takes for them to meet. And at this point, you might just say, okay, if they have the same acceleration, then they're going to meet in the middle. And you'd be right. But let's prove it this one time, okay? And so, all right, so I'm just going to say, okay, so I'm going to take the magnitude of their displacements, which I'm going to call d for distance, and I'm going to say that the sum of those two distances is equal to the total initial distance between them. Okay, again, not displacements, but distances. So instead of using x for displacement, I'm using d for distance. All right, so we plug this in. All right, we cancel it out because both these distances start with 0 based on the absolute value. They both also start from rest. All right, so then we can simplify this, and we get our 1/2 a sub at squared and our 1/2 a sub bt squared. But of course, a sub b equals a sub a, right? So it's just 5 and 5. And that's going to be equal to the distance of 12. And now just numerically, I'm just going to simplify it. So all I've done is just combine these two terms into a single term. And then I'm going to isolate t, and it ends up just being the distance divided by the acceleration. Okay? That's it. And that's because they shared the same acceleration. And then inside the root. So it takes them 1.55 seconds until they meet. Okay? Now, if it asks for how long, that you would need to find that, right? So I didn't, but all right, now we're going to use that information, plug the time back in, and we can plug in either one of the displacement functions. I'm going to plug into the displacement function, the distance function for a, this guy over here. All right, so 1/2 acceleration times the time squared, and I get 6 meters, and then I know that must be the same for b because everything else is the same for b. It's the same acceleration and the same time. Right, so they both travel 6 meters, they meet in the middle. They meet in the middle because they experience the same force and they have the same mass. Thus, they both had the same acceleration. Okay? Okay, so there we have it. Even though one of them just held on, they both moved. Okay? And that's because massless rope, Newton's third law. Okay? And they met in the middle because they had the same mass. But what if they don't have the same mass? Well, they won't meet in the middle anymore, right? Okay? So same situation, two people of unequal masses are each standing on perfectly smooth ice, I should say similar situation, and are holding two ends of a taut rope of negligible mass. Okay? One person with a mass of 50 kilograms pulls with a pulling force of 350 newtons, and at the same instant, the other person with a mass of 100 kilograms simply holds on. So see what's different here? We got a 50 and a 100. Okay? The rope is still 12 meters long. How far will both people travel by the time they meet? Okay? So very similar picture. The only thing I've done here is I define MA as 100 and MB as 50. And I could have set either one, okay? All right, but since the person that's holding on is the one that weighs more, I didn't want to change the name of these vectors, so I just made them the 100, okay? Same coordinate system, positive x to the right. All right, so notice I start with the same statement of Newton's third law, and this is between two objects, person A and the rope, and person B and the rope, okay? All right, well, since the rope is massless, that tells us that FP equals F hold, which means that FAB must equal FBA. Okay, see? No change there. All right, now we're going to go and find their accelerations. Okay, so we're going to find the net force on A, which is just FAB, and that's going to be equal to MA, A sub A. All right, so that's going to be 350 newtons divided by 100 newtons, or 3.5 meters per second squared. But for B, well, B is, first of all, negative, because B will be moved in this direction, the negative x direction, and they don't weigh as much, or don't have as much mass. And so then their acceleration is twice as large in magnitude and negative, so it's negative 7 meters per second squared. Okay? Now I'm going to set up a way to then find out how much time it takes for them to meet. Notice I wanted to mix it up, so an alternate way of solving the kinematics portion. So instead of taking the sum of their distances, I'm actually taking the difference between their displacements, which must be 0, because they have to at some point meet. Okay? And if I take the difference between their displacements, then, and I go ahead and just continue to solve for it. Okay, notice here that I just have AB as just a variable. I haven't plugged it in as negative or positive yet. So here it's subtracted just because of the distributing the negative. All right, and I'm just cleaning it up a bit. And then I get a nice general statement here, and we can see it's 2d over the difference between the accelerations is the time for them to meet. Okay, so that's sometimes going to be the advantage of not plugging in numbers right away. You can get useful symbolic expressions. Then I do plug in the numbers. So I plug in 12 meters for D. I plug in the positive acceleration for A and the negative acceleration for B, but minus a negative makes it positive. All right? And so then when I actually solve that, I get 1.51 seconds. And that's so interesting, right? That by just making one of them less massive, the time for them to meet has reduced. Just a little bit. It went from 1.55 seconds to 1.51 seconds. That's not a rounding error. It actually takes less time for them to meet. But of course it does, because the whole system is less massive. Before, the whole system had a total mass of 200 kilograms. Now the whole system has a total mass of 150 kilograms. So that whole system is easier to move. It takes less time to do so. Right? So there's kind of like fascinating ways to think about this. Okay, that would be a Newton's second law kind of problem. And then we just want to use the time to find, now I'm going to go ahead and find the distances, because the problem kind of asks for how far they both went, not like, what was their displacement or anything like that. And the way it's worded, it does sound like it's asking for a distance, and I wanted to stick with that, right? And so then if I'm finding the distance, notice then I drop the negative, and I find then that person A, that is the more massive person, of course, moves 4 meters, and person B, the less massive person, moves 8 meters, okay? Now, of course, person B does move in the negative direction, but if we just care about their magnitudes, it's 4 and 8. And look at that, 4 and 8, that just means that the person that's twice as massive moves half as far, right? So the numbers totally make sense. All right, so finally the last example, and I don't want to get into the weeds too much on this one. This is basically, there's a lot of moments sometimes where I'm teaching where a student says, wait, this can't be right. What if you do this, And so in this case, they said, what if the two people pull with different forces? What if one of them doesn't hold on? What if they both pull? And in fact, what if they both pull, and they pull, as I said, with different forces? Well, that will break the system. And it doesn't. It doesn't break the system. It does make it a bit harder to solve, but we can follow very similar rules. We just have to use a bit of extra considerations. So I'm going to go through it, but don't worry about this one too much. It was kind of a what-if problem, okay? So two people of equal mass of 100 kilograms, and I decided to at least keep them equal mass again, are standing on perfectly smooth ice and are holding the two ends of a taut rope of negligible mass. Okay, that's all it's saying. One person pulls with a pulling force of 300 newtons, while at the same instant the other person pulls with a force of 200 newtons. If the length of the rope is 12 meters, how far will both people travel relative to the ice, there's some new wording, by the time they meet? Okay, so let's see. So here's the situation. All right, here notice I have F pull A and F pull B now, because they're not the same. There's no hold. Okay, all right, so F pull A is 300 newtons and F pull B is 200 newtons. Now the first thing I'm going to do in order to solve this problem, because when I look at this, I immediately, having solved a lot of problems like this, I look at it and say, well, okay, if I think about the total system, the total inertia, as I mentioned before, we had a total inertia of 200 in problem 3, and a total inertia of 150 kilograms in problem 4, right, or example 4. Well, in this one, right, it's 200 again, but what's the motion of the total system? Well, last time, right, the motion of the total system was 0. So in other words, these two people were not moving relative to the ice. They're moving relative to each other, right? But as a MA plus MB system, as a total mass system, there was no motion, okay? And that's because F pull equals F hold, okay? But look here, F pull B does not equal F pull A. So that means that the people together are actually going to move relative to the ice. As a pair, they will accelerate relative to the ice. They will also accelerate relative to each other. And that's the rub, right? All right, so let's go through it. So we need to consider the acceleration of both people relative to the ice, as I mentioned, okay? So we then consider the net, F net x, and this would be the net force acting on the combined pair of people. So it's 200 newtons in the positive direction, because that's F pull B. All right, yep. And then minus 300 newtons in the negative direction, which is F pull A. All right, and that's going to equal M total, which is just going to be 200, times the acceleration of both of them relative to the ice. And they're both going to have the same acceleration relative to the ice. They have to, okay? All right, so then we go ahead and solve for that, and we find that either one of them, or both of them, depending on, that's both are valid ways to think about it, have an acceleration relative to the ice of negative 1.2 meters per second squared, okay? So they're moving together in the negative direction, because that makes sense because that was the bigger pull in the negative direction, at a rate of 0.5 meters per second squared. Okay? Okay. So then we're going to take our next step and consider the net force on the rope, which is 0. And that just means, right, so that's just telling us that FAB equals FBA. So that's great because that's that whole perfect transmitter of force idea, okay? Because that's just saying that these two forces have to be equal to each other. So that idea hasn't changed. And that'll actually be a real kind of fallback truism of forces. And we'll learn later that this idea, FAB and FBA, we can really call it tension. And it basically just says that the tension on either end of the rope has to always be the same because the rope is always massless. Okay? Thank God, right? If you want non-massless ropes, take Physics 40, although those are rare problems because they're inherently tricky. Okay? All right. So let's look at the next step. So we can consider the forces on an individual person to find FAB equals FBA. Okay, so we just want to find that connecting force between them. Okay, the reaction force between person A and person B. Okay, so I'm just going to consider person A since I'm reading from left to right, and they have a force FAB, and then they've got the pull, which I know is 300, and it's negative, right? That's why I'm subtracting from it, because when I think about my net forces, I include the sign, and then I'm going to set that equal to mass times A. And here, notice A, I haven't plugged it in as negative yet. I will once I actually plug in numbers. Okay. All right. So then I'm just going to solve for that connecting force, the force on person A from person B. Okay. And it's going to have this form. All I've done is just move the pull to the left hand or the right hand side of the equation. And I plug in my values. So then I get 300 newtons. So that's the pulling force. Okay. And it's positive because I added it. It started as negative, but I added it to the right. And then I got my 100 kilograms times the acceleration. Here I'm including the sign of the acceleration. So there we go. I find that the force that connects the two people is 250 newtons. All right, and that's kind of cool because that's actually just the average of the two pulling forces. Now, actually, the reason it's the average of the two pulling forces is because they have equal mass. Okay, all right. So, and if you want to try it with non-equal mass, I actually did put that in one of the possible follow-up problems. So you're welcome to try this problem with non-equal mass if you want. Okay. It will all be all the same steps. Okay, so then, and the acceleration relative to each other is found by, considering the net force on just one person. So what are we doing here? Okay, notice here now I'm solving for the acceleration relative to each other, not the acceleration relative to the ice. If I want, so now I already know the acceleration relative to the ice, and I'm going to use it in the final step. But for this second to final step, I want to actually find the acceleration relative to each other because I don't know it yet. Okay, I just found the connecting force between them. Okay, so what does that look like then? Well, I just go in and they both have the same mass, 100 kilograms. So that means that the acceleration of A is 2.5 meters per second squared because it's moving in the positive direction. Okay, relative to B, and meanwhile the acceleration of B relative to A is negative 2.5 meters per second squared. Oh, so they both have the same acceleration. That means they're just both going to travel 6 meters, right? All right, well, let's check, right? Well, actually, we don't have to. I'm going to say we already know, right? We already know that equal accelerations mean equal distance relative to each other. That we already solved that 2 examples back. So they're definitely both going to move 6 meters relative to each other, okay? And we can find the time, okay? And so in this case, we're going to find that the time it takes them to move that distance is... Okay. Yep. Is going to be 2.19 seconds, right? Because they have to accelerate at that rate. I'm just trying to think. Oh, right, because it's a different force. So I was like, wait, why is this a different number? Because it's a different force. So it takes them 2.19 seconds for them to reach. Okay. Okay. Good. All right. That makes sense. So they're going to meet in the middle. They're both going to travel 6 meters relative to each other. That's how I knew to plug in 6. And then all I did is just find the time for them to meet based on the acceleration that they both share in magnitude at least. Okay, all right. So this is a distance, not displacement. Okay. So now what am I going to do with that 2.19 seconds? Now I'm going to use it to find their displacement relative to the ice. Last step. Thus, relative to the ice. Okay. Squeeze this in on the bottom of the page. The displacement of A relative to the ice is going to be equal to 1/2, because it's just the kinematic equation, A total, okay? Or you can think of this as just A relative to the ice. Well, A relative to the ice is the same as the system relative to the ice plus the system's acceleration relative to the ice plus the person's acceleration relative to the system, okay? So this is just a relative acceleration equation, right? But I'm just putting it in this intermediate step, okay? And so we know the values. We know that both of them accelerate relative to the ice, so the system accelerates relative to the ice in the negative direction at 1/2 meters per second squared. And we know that person A accelerates relative to the system in the positive direction at 2.5 meters per second squared. Thus, relative to the ice, person A is going to move 4.8 meters. And that makes sense, right? Because together, collectively, they're drifting this way. But meanwhile, A is moving towards B that way. So that means that A will actually move in the positive direction because they're moving faster in this direction, okay? And they're going to, they'll meet up and they'll both travel 6 meters relative to each other, but in that time, they're drifting, right? You see that? You can visualize that, okay? And let's think about B. B is all negative, right? So they got the negative acceleration system, plus B is accelerating towards the left as well. So they're actually going to move negative 7.2 meters relative to the ice by the time they meet person A. Okay? So yeah, having them pull at different strengths does definitely complicate the system, but it's still solvable, which I hope is reassuring. Okay? So there you have some examples, some more introductory than others, right? But definitely a good introduction to forces, and certainly just the beginning of what you're going to see this week in terms of all these examples, lots of chances for practice, thinking about what it means to solve a problem involving forces. And of course, you've got some extra problems that you can tackle if you for this set of lecture notes as well as the next few. And thank you so much for watching this lecture video, and stay tuned for more. I await any questions that you send my way. Bye for now.